Hi everyone, my name is Adam Slavney, one of the 2019 Arnold O. Beckman Postdoctoral Fellows. For the last 3 years, the Arnold and Mabel Beckman Foundation has funded my work in the Mason Group at Harvard, and I'm indebted to the foundation for their support. Let me tell you a little bit about what I've been working on. Every air conditioner, heat pump, and refrigerator on the planet relies on hydrofluorocarbon gases, like the one shown here, to move heat from one location to another. While these gases are effective refrigerants, they are also extremely potent greenhouse gases, several thousands of times more potent than CO2. Every air conditioning system inevitably leaks small amounts of these gases into the atmosphere, where they are directly responsible for around 3% of global warming today. That's more warming than caused by the entire aviation industry. Eliminating these refrigerant emissions has been identified as one of the top 5 most impactful climate solutions that we can implement today. My research into the Mason Lab focused on replacing these hydrofluorocarbon gases with a solid. Solids are non-volatile, so they will basically never end up in the atmosphere. Unfortunately, most solids are bad refrigerants because they are very incompressible and insensitive to pressure, and pressure is what we use to drive the refrigeration cycle. In collaboration with my colleague Jin-Young So, I found that a certain class of solids, layered halide perovskites, undergo a solid-solid phase transition near room temperature with a very large volume change. This large volume change makes these materials very sensitive to pressure when there are temperatures close to that phase transition, and that makes them useful as refrigerants. Let's take a closer look at what's happening in this material at the microscopic level. This phase transition is very analogous to the melting of wax, particularly if we just zoom in on the organic part of the structure. These long carbon chains on the left are packed in a very well-known static ordered arrangement that looks very, very similar to solid wax. However, when you heat this structure up, those carbon chains go from an ordered static state to a highly dynamic disordered state that could almost be described as a fluid. However, because this fluid-like structure is contained by these stiff, rigid organic layers, the overall structure remains a solid on both sides of the transition. We can use this phase transition to run a refrigeration cycle, and that works as follows. The perovskite starts on the top right in its disordered state. It can then be pressurized, causing it to transition into the lower volume ordered state, and that heats it up in the process. We dump this heat outside and then release the pressure. This causes the perovskite to revert back to its disordered state, cooling it down in the process. And we can now use this colder material to absorb heat from the room, cooling that room down and closing the cycle. The most critical part of this project was showing that it worked in the real world, and I was able to use the financial support provided by the Beckman Foundation to construct the first pressure-driven solid refrigerant prototype device, shown here, and demonstrate that we could actually cool something in the real world. I'm now moving on to found a startup company, Pascal, which will commercialize the solid refrigerant technology we developed at Harvard and work to eliminate greenhouse gas emissions due to refrigerants. In this way, I feel like I'm following in the footsteps of Dr. Beckman, taking a good idea born of fundamental scientific research and creating a technology available to everyone and for the public's benefit. I'm excited to see where the future takes me and sincerely thank the Arnold and Mabel Beckman Foundation for all their support.